reading group session today. So this is our logic and automatic reasoning. But today we're going to digress a little bit. So today's topic is actually about computation. Right? It's about computation. And there's a reason why we always talk about logic and computation together. So today we're going to talk about computation, and probably the week after or 2 weeks after, we'll come back to logic, and then we'll see why they're always talked about together, right? So, right, I need to share my screen. There we go. Okay, I think you can see my screen. Yeah, I can see it from there, so it should be working. All right. Let's go to this whiteboard. We've been developing in this reading group. Okay, you find some white space. This is a good space. Okay, so computation. Now, today's session is essentially a history class about computer science. And we're going to go back to the 1900s. We're going to go back to the 1900s. So back in about 1900, that's many, many years ago, there was one of the top mathematicians. I mean, back then there was no computer science. There's no computer, right? So there's no computer scientists. Back then they're called mathematicians. Right? One of the top mathematicians at the time is called David Hilbert. Right? So I'm going to write his name down. Name is David Hilbert. I think he's German. And he was like the Isaac Newton in physics. He's David Hilbert in mathematics. Right? He was one of the top guys in the world. And in around 1900, he collected a selection of mathematical problems. In particular, I think he collected 23 mathematics problems. And he thinks that those are the major problems to be solved in the next century. And that was in about 1900. 23 mathematics problems to be solved in the next century. He said those are the most significant ones. I mean, of course, there are thousands of them, but he thought those 23 are the most significant mathematics problems. All right. So most of those 23 problems are solved today. All right. Most of them are solved today, but there are a couple of them that are not solved. A few of them that are not solved. One of them, well, when I say not solved, there are actually a few of them that have been shown not solvable. Back then, not solvable is just not a thing, right? Because in the 1900s, everybody thought that every problem can be solved eventually. And if you cannot solve it, that's just because you haven't come up with a solution yet, or that's because we don't have the technology yet, right? But the belief was that eventually it will be solved. And there was this very famous quote from him. He found it from the book. So this quote was actually in Hilbert's one of his opening speeches, and this was in 1930. In 1930. So he said, for the mathematicians, there's a Latin word. It's called ignoramus. And it's related to ignorance in English. It roughly means we will not know, we do not know, and we will not know. Right? And he says this is rubbish. All right, he says, in my opinion, and also for all of the natural science, this doesn't exist. All right, so his belief was that everything can be solved eventually. All right, and he said the true reason why no one has succeeded in finding an unsolvable problem is that there is no unsolvable problem. Back then, nobody has found any problem that is unsolvable. By unsolvable, we mean it cannot be solved whatsoever. Right? So, back then in 1930, nobody has ever found any unsolvable problem. So everybody thought that, all the problem can be solved eventually. So he said his motto is actually, we will know and we shall know. Eventually we can solve it. And this is actually written on his tomb. If you go to Germany, this is actually written on his tomb. Quite interestingly, on the same day, so that was I think was I look at the notes, 8th of September 1930. There's another mathematician, and his name is called Kurt Gödel. Name is Gödel. And he gave another talk at workshop, right? And his talk is actually about one of the problems that David Hilbert proposed. And he said it cannot be done. So that problem is about probability. Okay, it's about probability. This is one of the major problems that David Hilbert proposed, and said this should be a problem we need to solve. And the details of this problem is that we want to develop some sort of mathematical theory such that we can prove everything about this theory, right? And we have two major criteria. So for those of you who have joined previous sessions, one of them is called completeness. Completeness says if you can express a statement in your logic, then you should be able to either prove that it's correct or prove that it's incorrect. All right, so you need to be able to either prove it or disprove it. All right, and then there's another one called consistency. Consistency says you cannot prove incorrect statements. You cannot prove contradictions. So consistency sort of means your theory is correct. And completeness means your theory is capable of proving or disproving a lot of things. So Hilbert's idea was we need to find such a theory that is able to basically express everything we have today in all of our mathematics, chemistry, physics, biology, whatever science. We need to have a theory that can express all of those statements, and we need to be able to prove or disprove things about all of those sciences. That was his vision, that one day we can have such a theory that covers everything, and it has to be complete, it has to be consistent, and we have perfect science. So Gödel came along in 1930. This is about 1930. All right, so Gödel proved this thing called his incompleteness theorems. So obviously, we're not going to go into most of the technical details of those. Today is a history class. So you can Google those terms if you're interested. But basically, his incompleteness theorem says if we have a logic system that is expressive enough to be able to talk about elementary, he called it elementary arithmetics, right? If it's expressive enough to talk about the elementaries, then it's not going to be both complete and consistent, which is a very sad result. And by elementary, the technical arithmetic he used was called Peano's arithmetic. If you're not familiar with Peano's arithmetic, you can easily search for it. And there's a Wikipedia page about it. So it's an arithmetic system that consists of a few axioms. And he called it elementary because it is indeed very elementary, right? So it is actually, it's just the arithmetic that you learn at primary school, right? So if you look at what's shown here, it's nothing special, right? It says axiom number 1, 0 is a natural number, right? Simple as that. Axiom number 2, for every natural number, the equality is reflective. So for every natural number x, x equals x. Right, it's very, very simple. And it's symmetric. So if x equals y, then y equals x. And it's transitive. X equals y, y equals z, then x equals z. Right, so those are all the most basic, right? Those are the most basic rules we have in arithmetics. And then there are a few more advanced rules, right? That allows you to do mathematical induction. But really, there's nothing special there, right? So it's basically, it goes probably, it depends on the education system, probably goes up to high school arithmetic, and that's as far as it goes, right? It's really simple. It's really simple. And Gödel said, if our logic language, our theory is enough to talk about those things, then it's not going to be both complete and consistent. If it's complete, then it's not consistent. It's going to derive some contradictions. It's going to derive some rubbish. And if you want to keep it consistent, then it's not going to be complete. But that means there are going to be things that you cannot prove nor disprove. There are things you just cannot do anything about. Right? It's a very negative result, but sometimes negative result tells us where our limitations are. All right, so that was one of the few one of the things in Hilbert's 23 problems, and the other problem is about computability. The other problem is about computability. And there was a word for it, so but it was written in German because Hilbert was German, and I'm not going to pretend that I can read German. Most of those German words are ridiculously long and hard to pronounce. All right, so I'm going to borrow from my quote. So the word is called, it's spelled as this whole bunch of things. So I'm going to write it down here. Okay, so that's in one word. And obviously, I mean, I guess we can split this up into two words. And it's about whether we can have an algorithm that is able to determine if a given statement is valid or not. Okay, so whether we can have an algorithm to do such a thing. Given any arbitrary statement, we want to know if it's valid or not valid. And you can see these two problems, they're closely related. Closely related. And this is so speaking about an algorithm that's not too foreign to us computer science people. And in computer science, we often talk about different computational models, right? And they're used to do different computations. So a generalization of this problem here is asking about a computational model, an algorithm, a way you can do computation such that given some input, it can always give you the output. It can compute things, right? And there have been, mathematicians again. I mean, today, if they, live today, we'd call them computer scientists. Back then, mathematicians who thought about different computational models, and one of the major things they considered was what is computational model that can compute everything. The ultimate, conceptual computational machine. And there were a few proposals. So again, the mathematician Gödel proposed something called recursive functions. Recursive functions, and they are not the recursive functions you use in programming, although I think conceptually they are related. But Gödel's recursive functions are different. Right? So it's not just a function that calls itself. So in programming, if we have a function that calls itself, we say the function is recursive. But in mathematics, there's a different definition. Right? So there's a different definition. And again, we're not going to look at all those technical details, but we can have a brief look. Right? Recursive function. Copy this one. No, it's not. This is the recursive function in programming. Going to find the recursive function in mathematics. So maybe I search his name and it will come out. Oh, okay. So maybe I can even search for this primitive recursive function. Surely that will, there we go. So it's defined by a few cases, right? Constant, successor, projection, composition. So you don't need to understand all of that, but it's slightly different than, a function that calls itself, right? So it's called recursive functions. And then two other guys. There were Pliny and Church. So they were American mathematicians back then. They proposed something called lambda calculus. It's called lambda calculus, and that's another way to do computation. And again, we're not going to go into details about what is lambda calculus, how to use it. So when Gödel proposed recursive functions, he didn't think that this is going to be the ultimate way to do computation, right? So he just proposed it because he thinks those are some natural ways to do computation. He didn't have any idea that those would capture everything that is computable, right? And in fact, when he proposed recursive functions, he thought that there are probably computable things that this set of rules cannot compute. And then when Kleene and Church proposed lambda calculus, they made it with the aim that this is going to be the ultimate way to do computation. This can compute everything that is computable, right? So they also looked at the literature. I mean, like today when we do research, you look at the literature review and they see this Gödel's recursive function. So they analyzed Gödel's recursive function, and they realized, oh, these two things they look completely different in the way they're presented. They do computation in completely different ways, but interestingly, they actually represent the same set of computational problems. So in other words, if given any problem, if you can compute it with recursive functions, then you can compute it in lambda calculus. So they established this equivalence relation, right? Although these two things are in completely different formats. So when you look at them, you wouldn't think they're equivalent, but they actually prove that in terms of computability, they are equivalent. And Gödel was not convinced. Gödel thought, okay, maybe something's wrong. I mean, let's be more careful. So they actually, because they live in the same era, so they actually invited Gödel to their university. They had a workshop, they talked, and Gödel was not really convinced. So Gödel thought, okay, maybe there are some things that are computable, we just didn't capture that in our system. And then there was another guy called Alan Turing. So if you've seen the movie, there's a movie about him. And I think nowadays he's also printed on the notes in the UK. So he's regarded as one of the founders of computer science, right? And Turing proposed something called Turing machine. Obviously, he didn't call it a Turing machine. People after him called it Turing machine. All right, and he wrote a paper about it, and that was in about 1936, I believe. Have a look at the notes. Yeah, I think it was about 1936. So he published a paper, and the paper is literally called uncomputable numbers with an application to this exact problem. Was aiming to solve this problem, right? And was published in 1936. So back then, Turing was 23 years old, right? So he hasn't even he hadn't even completed his PhD, and he was 23 years old. It's very young, but obviously he's very smart. And then now, when he did his PhD, his PhD supervisor was actually Church. Right, so you see all those guys are connected. So Turing was British. He went to the US to do a PhD. His PhD supervisor was Church. So when those guys, the top guys in the world, Gödel, Kleene, Church, they looked at Turing machine, they finally thought, wow, this is something that actually can convince us that it can compute anything that is computable. And it is presented in such an intuitive way. So when Gödel looked at the presentation of the Turing machine, he finally believed, okay, this is going to be the thing, right? This is going to be the computational model that can compute everything that is computable. And later on, people actually proved that in terms of computability, all the three proposed models, so recursive functions, lambda calculus, and Turing machines, they're actually equivalent in terms of computability. And nowadays, this is basically, so Turing machine is basically the golden standard now. So if we say something is Turing complete, we say it can compute everything a Turing machine can compute. Right? In other words, we believe that it can compute everything that is computable. We call it Turing complete. So, so at this point, I may briefly introduce what a Turing machine is. And that's only, so I'm not going to introduce, recursive functions. I'm not going to introduce lambda calculus. I'm going to introduce Turing machine because exactly, its presentation is very easy to understand. All right, so a Turing machine is essentially a state transition machine with some sort of storage. Okay, so if we draw it, we shouldn't be too unfamiliar with state transition machines. If I want to draw a state transition machine, I would use circles to represent states. S0, so initial, let's say that's the initial state, and it has some transitions. So it goes to some other state, let's say S1. S1 may go to some other state, let's say S2. May go back, let's say it can have any transitions between states. All right, so maybe another one, let's say a bunch of states, a bunch of transitions. Sometimes we want to define a state to be the initial state. Sometimes we want to say some state is final state, and that's where the computation ends. All right, state transition. Okay, so that's pretty straightforward. And Turing machine adds one thing on top of it, and that's it's a storage. In today's world, we call it memory in our computers. Because state transition machines, so technically they're called finite state machines or finite state automata. They don't have any anything that can help you store things, memorize things other than states. But you can only have a finite number of states, so you can only have a finite number of things you can remember. And you can only do transitions between states. You cannot read and write. So Turing said, okay, I'm going to add something on top of it. And the one thing he adds on top of it is called a tape. Right? Back in the 1930s, tape is something people used to record things. All right, so now you can imagine the state transition as a unit, as a module. All right, and this module has a pointer. It has a pointer, and this pointer points to a tape. Okay, so this tape has many cells. Right, and this tape is infinitely long. So it goes infinite to the left, it goes infinite to the right. It means you can store as many things as you like. And this machine can do a few things at every state transition. Okay, so every time you want to transit from one state to another state, or sometimes you can even transit from one state to itself. So you don't move to other states, you move to yourself. All right. So every time you do a transition, you can read something from the tape. Okay, so you can do a read, or you can do a write, or you can do nothing. You don't read and write. You can do nothing. Okay, so you can modify the tape, and you can move the pointer to the left. Okay, you can move it to the left. You can move it to the right, and you can make it stay the same. Yeah. So you can imagine this tape is the memory on our computer. Right? So you can move one cell to the left, you can move one cell to the right, you can make it stay still, and then you can read it, you can write, or you can just keep it as it is. So this is basically Turing machine. Right? This is basically a Turing machine. State transition plus memory. Plus a memory that you can read and write, and the memory is infinitely long. Okay. And this presentation is so intuitive that when Gödel saw this, he said, okay, I am convinced that this can compute everything that is computable. So we can actually compare this with our computers today. Right? If you want to have a comparison with our computer today, our computer usually, when we talk about today's computer, we talk about the von Neumann architecture. The von Neumann architecture, actually von Neumann is a colleague of Gödel. And a lot of them, they actually worked at Princeton University in the US back then. So they actually had an institute called the Advanced Something Institute. And they had, the major guys from every field there. Anyway, so if we look at today's computer has something called a CPU. All right, so the central processing unit. So you can imagine this state transition part is a CPU of the Turing machine. Okay, and today's computer would have something for the I/O, for the input and output. So the input would connect with your mouse and keyboard, and the output would connect to your monitor. All right, but those are not really of concern in terms of computability. All right, what's really important about computability is your computer would have some sort of memory. Okay, and in the von Neumann architecture, you actually have memory of different types. So there's the random access memory. So that is the memory that we usually say, how much RAM do you have on your computer? Okay, and then there's also the hard drive. Okay, and of course, sometimes RAM is not fast enough. So between RAM and CPU, we also have the cache. So those are all different forms of storage. Okay. So your CPU access those storages in a certain way. And that's just as in Turing machines, state transitions access the tape. So there's actually proof that given any computer that we have, right, we can always construct a Turing machine that does the exact same thing. You can imagine this is quite straightforward, except, if you look at the formulation of a Turing machine, it actually doesn't talk about how fast it computes. Right? So it does state transitions, but it never tell you how fast can you move from one state to the next state. Right? It can do read and write, but Turing never specified how fast it can read the tape or write the tape. And the tape is infinitely long. Right? So in a sense, it can compute as fast as you want. It can store as many things as you want. And those are the capabilities that today's computer cannot have. Right? So today's computer can only be an approximation of a Turing machine. It cannot really be the real Turing machine. All right, so computers are only approximations of Turing machines. But on the other hand, a Turing machine can simulate everything you can do on a computer. Okay, so really, really powerful. And then, so we haven't mentioned this computability problem, right? So the idea was that Turing machine can compute everything that is computable. But then there are some problems that Turing machine cannot give you any answer at all. And there are also problems that Turing machine can only give you part of the answer, but not the other part. So theoretically, there are actually limitations to Turing machines. And that's where, people realized there are actually problems we cannot solve, unsolvable, right? So before 1900, nobody actually found such problems, right? And we're going to illustrate one of those problems with the Turing machine. So the problem is, so we're going to illustrate, it's called the halting problem. Of the halting problem. The halting problem says if you're given a Turing machine, you're given an input that the Turing machine would accept. Well, not accept. You give an input to that Turing machine, and the question is, will this Turing machine eventually stop computation, whether it will halt or not? Okay, so the formulation of the problem is given two things: a Turing machine, I just call it a TM. So an instance of that Turing machine, right? So let's say M, we call it M. And also an input, let's call it W to M. Decide whether M halts on W or not. Okay, so this is the halting problem. Okay, now we're going to think of this from a programming perspective. Most of what we do these days are programming instead of constructing Turing machines, but we know that they are equivalent. Right? So if you can write a program, there must be a Turing machine that can do whatever your program does. So whenever I say a Turing machine, you can imagine that is a program. And in fact, when I talk about Turing complete, right, so the concept of Turing complete, so being able to compute everything that a Turing machine can compute, there are lots of instances, right? And in fact, most of the programming languages are Turing complete, right? So it doesn't matter if you use Python or Java or C++, C#, even JavaScript, most of the programming languages are Turing complete. So they can compute everything that a Turing machine can compute. In other words, they can compute everything that is computable. Okay. And if I can actually narrow this down. So if a programming language contains the following elements, it would be Turing complete. Okay. So it needs to be able to do variable assignment. You need to be able to assign some expression or value to a variable. It needs to be able to do sequential composition, so you can do this statement, then do the next statement. That's elementary, right? So that's usually the semicolon to write in most programming languages. It needs to be able to do branching. So if, in other words, if statement, if something, then something else something, right? That's something that you can imagine most of the programming languages have. And then it needs to be able to do loops. So doesn't matter if it's while loop or for loop, most of the programming languages would have some way to do loops. Or if it doesn't have loops, recursive function calls are just equally good. Okay, if you have those elements, then your language is Turing complete. Right, all the other things are icing on the sugar, icing on the cake. Right, it makes it easier to program certain applications. But from a computability point of view, they are equally good. So most of the programming languages are Turing complete. And in fact, you'd be surprised, there are a ton of other things that are Turing complete. So, so somebody has proved that Microsoft's PowerPoint software, the one that you use to make slides, it is also Turing complete. So you can use it to do any computation you like. Right? Excel, obviously Turing complete. Even Minesweeper, the game that you play to select where is a mine, where is not a mine, it can be coded in, it can be used in a way that can compute every computable problem. Right? And more complicated games obviously would be Turing complete. So Minecraft, if you play Minecraft, it is Turing complete. Right, so a ton of them are Turing complete, but I guess for today's purpose, you can just imagine when I say a Turing machine, you can imagine that's some piece of program that you write. Right? And I'm going to draw Turing machines as modules because you can write programs that contain other programs. Okay. So we're going to, sort of simulate this proof that the halting problem is undecidable. There's no way to decide the halting problem. So you can imagine halting problem is actually asking, given a program and an input to that program, and you want to decide if that program eventually terminates. It's the same problem, right? But obviously sometimes there'd be some sort of infinite loop or some other bug in your program. It may run forever. So the answer to this question is there's no way to tell. Generally, there's no way to tell. Right? So that's why debugging a program is so hard. Okay, and we're going to prove that by contradiction. Proof by contradiction. So what I mean by proof by contradiction, we assume the opposite, and then we show that we can derive some contradictions. We can derive something that is inconsistent. And that means what we assume is wrong. So the opposite is true. Okay. So we're going to assume that it is computable. We're going to assume that there is a Turing machine that can decide this problem. There's a Turing machine that can decide this problem. All right. So we're going to call this Turing machine H. That can decide the halting problem. Okay, we're going to assume that this Turing machine exists. And we're going to use this Turing machine in this strange way to show that there's a contradiction. And then we know that this assumption is wrong, so such a Turing machine doesn't exist. Therefore, such problem is undecidable. All right, so this is the rationale behind the proof. So we're going to construct another Turing machine. Okay, we're going to construct another Turing machine. And this Turing machine, we call it P. We call it a P. Okay, and this Turing machine is going to use this hypothetical Turing machine H as a component. Okay, so we assume that H can solve the halting problem. That means if you give it a Turing machine and its input, H will tell you whether it stops or not. Okay, so let's say if you give it some Turing machine M and some input W, H can tell you whether it halts. Yes means it halts. No means it doesn't halt. All right, we assume that such a Turing machine exists. Now, when I write this input M and W, you can imagine M is a piece of program. All right, a piece of program is just, you can imagine that's just a big string. And W, its input is also a string. So you can do some string concatenation. So that becomes, so this pair of M and W becomes one input, right? That's totally legitimate. Okay, so the input to H is just one big string that is, that consists of a pair of another Turing machine M and an input W to that Turing machine. Okay. But the input to our Turing machine P is just one string. Okay, it's just one string. So we're going to have some data pre-processing there. So what I'm going to draw at the beginning is we're going to have another Turing machine. Okay, and what this Turing machine, I call it C. All it does is it does data pre-processing. So if you give it an input W, it's going to make it a pair. It's going to make it W, W, make it a pair, two W's, concatenate it together, and send it to H. Okay, send it to H. And if H says it's going to terminate, then I'm going to write another Turing machine. Right, so I'm going to call it M. I'm going to call it N. And what this Turing machine does is it does an infinite loop. All right, so this N, literally, what it does is, imagine that is a program, well one, do nothing, and it's going to loop forever. All right. So this Turing machine N loops forever. Okay. And if H says it doesn't terminate, then P1 will accept and say it terminates. All right, so this is our construction of a special Turing machine P. And now the question is, what if we ask the question, does P halt on P? So if you give this Turing machine P its own code as input, does it terminate? Yes, this is the question. And if we look at the construction, if you give it P, here will be PMP. So it will ask the Turing machine H, does P halt on its own code as input? And if H says it halts, then P will loop forever. So you get a contradiction. If H says it doesn't halt, then P will eventually stop. And you have another contradiction. So it doesn't matter which case it is, you always have a contradiction. Okay. So that means something's wrong with our assumption. What's wrong with our assumption? Our assumption is that a Turing machine H exists that can decide the halting problem. The reality is halting problem cannot be decided. Okay, so this is our proof. And this is very strange proof, and it involves some self-reference. It involves some self-reference because we're constructing a Turing machine called P, and we're asking if you take its own code as input, will P terminate? And sometimes this kind of thinking is very convoluted, and it just breaks people's minds. But anyway, so this is arguably one of the earliest problems that people have found to be undecidable. All right, so it means there's a proof, the proof we have right now that shows there's no Turing machine that can solve it. Right? And it doesn't matter how fast your computer goes, because you've seen the concept of Turing machine. It can compute as fast as you like. The performance is not an issue. Right? It doesn't matter how fast your computers can compute. You can bring it some computer 100 years later. This problem is still not going to be solvable. Or it's not going to be solvable forever. So we've introduced the first problem that is uncomputable, undecidable. Okay, I think that's pretty much it for today's session. So we've sort of established what is a computational model, what can it do, and what can it not do. Well, more important thing is to know what can it not do. So you know what can it do. You can write some program, right? So whatever your program can do, a Turing machine can do. So it's important to know what your program cannot do. Right? So you can never write a program to detect if some other program terminates or not. It's not possible. You can write debuggers to debug some other problems, or you can debug the same problem but in very specific cases. Right? So you can write a program that checks if program has loop. If it doesn't have any loop, then surely it will stop. But you can't really check it for the general case. Right? So the general case is undecidable. All right, so I think sometime later we'll link this to logic. I think that's all for today's session. Stop screen sharing. You can stop the recording.
What if the problem processing is longer than tape, like the length of the tape?
I mean, the tape is infinite. It cannot be longer than something infinite, can it?
Is it a tape? If we know, like 1980s, like
yeah, the cassette tape, something like that. You can imagine, except that the one on Turing machine is infinite. In real life, you can never have anything that is really infinite. I mean, today's computer has really large RAMs, but it's finite. You can have 100 gigs RAM, but it's still finite. Right? The items in the universe is finite. So you don't really have anything that is infinite. I mean, Turing machine is just a conceptual design. I mean, practically you cannot have something as good as a Turing machine, right? And that's why I say computers can only approximate Turing machines.
binary tree?
It may not be binary though. I mean, it can do arbitrary transitions, so it can form cycles. You cannot have cycles in binary trees.
So,
You can have loops.
yeah,
That's why you can have loops in your program. So you can do a lot of things. You can do a ton of things. They look similar. Yeah, they have similar structures.
I thought there should be like big difference.
And
Conceptually,
conceptually, they're actually quite similar. By other architecture, I mean, what sort of architecture you're thinking about?
your lecturing should kind of be every concept. Yeah, I agree.
Okay, yeah, maybe think about what you wanted to say. Yeah, yes, we can stop today's meeting and stop recording.